This is part 2 of our review of differential equations. I hope you've tried these practice problems first. If not, pause the video and try them on your own. All right, matching slope fields here. I think one of the things we want to watch for is when we have slopes of 0 and when we have slopes that are undefined, and when we have slopes of 1. Those are the easiest to look for. So you'll notice the similarities here. So what A and B share in common is that if y is equal to x, then dy dx will be equal to 1. And look at what C and D share in common. They are opposites. So if y is equal to the opposite of x, then dy dx would be equal to 1. So let's highlight here our 45-degree line. So notice here that we have slopes of positive 1 on the 45-degree line. And here we have slopes of 1 on the negative, or on the 135-degree line. So we have already narrowed down that 3 and 4 are going to match up with C and D, and Roman numerals 1 and 2 will match up with A and B. So now what else can we narrow down here? If we look at A, we can see that x cannot be equal to 0, so our slopes would get vertical as we get close to x equals 0. And if y is equal to 0, then dy dx is equal to 0. So those are two easy things to look for. So on the horizontal axis, we should have horizontal tangent lines, and on the vertical axis, we should have no slopes. So do you see our horizontal tangents and our no slopes going because they get vertical right next to 0? So this is going to match up with A. And likewise, in our second problem, notice that if x is equal to 0, then dy dx is equal to 0. But we have the restriction that y cannot be 0. So on our horizontal axis, there are no slopes, and the tangent line should get vertical when we're close to that horizontal axis. And when x is equal to 0, that's our y-axis, we should have 0 slopes. So you can see how that matches up here. So this is our graph B. All right, so then if we look at similarly for C and D, here we can see that x cannot be 0, so we're expecting to have the no slopes on the vertical, and y equals 0. If y is equal to 0, then dy dx is 0. So on our horizontal axis, we have the horizontal slopes, and on the vertical axis, we have the no slopes. So this is going to be our graph for C. And I think you've got the idea here. If x is 0, then dy dx is equal to 0. Now that's not the only way that you could figure these out, but it's certainly the thing that might come to mind first. And y cannot be 0. So on the horizontal, we're going to the no slopes, and on the y-axis, we have our horizontal slopes. So this worked out nicely for graph D. All right. Here we have a function f given in the graph. So this is the graph of f. And by definition, function g is an accumulator. So g is accumulating the area from 0 to x under this graph. So question A says find g of 3. So g of 3 by its very definition is the area from 0 to 3 under our graph of f. So we would want to take these areas. So here we have 1/4 of a circle with a radius of 2. So 1/4 of 4 pi is 1 pi. And down here we have a triangle with a base of 1 and a height of -1. So that explains why that area below the curve there is negative. So we've got pi minus 1/2. Question B, find all values of x on the open interval at which g has a relative maximum. Justify. All right, so we could say, and notice, by the way, here we're going to use our fundamental theorem. Notice that when we do the derivative of the accumulator function, we get f of x. So this is not only the graph of function f, this is also the graph of g prime. So we'll use that all the way through the problem. So I know that g, I'm going to use the first derivative test theorem, g has a relative max when g prime of x, and now you must justify that it's the same as your graph of f, changes from positive to negative at x equals 2. So there's the only place on the graph where the function f or g prime changes from positive to negative. All right, and then for part C, write an equation of the line tangent to the graph of g. So for any tangent equation, we would need a point of tangency. So we want our x coordinate to be 3, so we want tangent to g. So g of 3 happens to be what we've already done in part A. That's often a pattern in a free response question. And we need to know the slope. So the slope would be g prime of 3. And by fundamental theorem, we just decided that g prime is the same as the graph of f. So f of 3. So we simply need to read this point here. So at 3, we have a y-coordinate of -1. So that y-coordinate on f is the same as our g prime value. So our tangent line, and we can leave this in point slope form, and you could distribute that negative sign. I'm going to leave the parentheses so that you know where it came from. So y minus y1 is equal to the slope times x minus x1 is our value 3. All right, and then for part D, find the x-coordinate of each point of inflection of graph g. So we're not talking about graph f, we're talking about the function g. So all we have available to us is g prime. My first thought is that function g has an inflection point when g double prime changes signs, because that's where concavity changes. So now I have to think backwards and say, well, when would g double prime change signs? That would be when g prime changes from increasing to decreasing, or decreasing to increasing. So when do the slopes of g prime would give you the values of g double prime. So when it changes from increasing to decreasing right here at 0, and when it changes from decreasing to increasing right here at 3. So now we need to put that in your own words. G has inflection points at, and I'm going to be very specific here, at x equals 0, where g prime of x equals f of x. You could use the letter t, by the way. It doesn't matter. Out of habit, I'm using x. Changes from increasing to decreasing. And at x equals 3, where g prime of x equals f of x changes from decreasing to increasing. Could you put those together with a statement like increasing to decreasing or vice versa? I suspect that would be fine. I might be over careful because we know that every one of your test readers is looking for you to be very specific with your application of theorems and justification. So, when in doubt, be more specific. All right, question 23. So we have a differential equation and its slope field. So part A, we are to draw some solution curves. So through the point 0, 1. So let's find 0, 1, and that looks pretty simple. That looks like a constant solution. And for part B, we want the solution curve through the point 2, 1. Well, that point 2, 1 is also on that same constant solution. So notice when you look at the differential equation, dy dx equals 0 when y equals 1. So y equals 1 is one of the solutions. So actually I could use my vocabulary better, is a constant solution. It's not the only solution, but it is a constant solution. All right, but we'll notice something different happening in part 3, I'm sure. Here we want to find the graph through the origin. So let's follow the tangents, and we reach equilibrium here. We level off. This looks like a logarithmic or an exponential function upside down. So notice that the constant solutions aren't the only solutions. All right, so now in part B, now we actually have to separate the variables and solve for each of the conditions in part A. Compare your answers to the ones you produced in part A. So are we expecting for parts 1 and 2 that we're going to come up with the equation of this line? The equation of that line is y equals 1. So we should already be expecting an answer for these two parts. We should already expect the answer y equals 1. So let's hope that our algebra checks out there. So I'm going to go over here so I have some space to work. So our differential equation is dy dx equals 1 minus y. So how can I separate the variables? I can divide both sides by that binomial and move the dx to this side. Oops, I forgot to write my dy there. And then we want to integrate both sides. So we would have here the natural log of 1 minus y, but there would be a chain rule. So we would need to have a negative inside and outside to make that work. And over on the right-hand side, you could put a 1 here if you wish. What is this the derivative of? It is the derivative of x. And then we would add a constant. And I think I'm going to simplify that right away by multiplying the other side by negative. So I'm going to make this a c2 minus an x. How come I don't have to make the constant negative? Because it could be any constant. And then I'm going to exponentiate both sides. So remember that this is going to become just our 1 minus y. And here we're going to write this as e to the constant, and then plus an e to the negative x. And this term is just a constant. So you can skip right to, oops, did I want this to be a multiply? Sorry. When do you add or subtract the exponents? When you're multiplying. That was kind of a bad mistake there. So c times e to the negative x. And now for, so this is our general solution here. And now we want to do 3 particular solutions. So in part 1, we did the point, the solution point was 0, 1. So let's find out what happens if we put 0, 1 into this function. And we like this because the absolute value of 0, we don't need that absolute value anymore. And this will be the opposite of 0, so that term is just a 1. So we will have 0 is equal to c. So our solution curve, when c is 0, the right-hand side becomes 0. So we have this equation. When c is 0, do you see how that right-hand side simply became 0? All right, so now this absolute value isn't necessary. And does that look like a 1 or an absolute value? That should look like a 1. So we'll move the y. And that was the solution we were expecting, right? We were expecting that constant solution. All right, in our second part of the problem, we were using the solution point 2, 1, and we're expecting to get the same answer here. So again, let's take our highlighted function, and we're putting 2, 1 in here. So as expected, we get a 0 equals this. So c must be 0. So we're right back where we were. So as expected, 1 and 2 gave us constant solutions. And then we expect a different one for part 3. The 0, 0, remember our purple graph, now we're expecting, I would think, a logarithmic or an exponential function that could be flipped, an exponential function. All right, so we're going to use the point 0, 0 into our solution curve. So now we have 1 minus 0 is equal to c e to the negative 0. So this is just a 1. So our value of c is 1. So now we have absolute value of 1 minus y is equal to e to the negative x. And what about these absolute values? Well, let's look at what we were doing here. Our graph can't cross over. It reaches that equilibrium, so notice that y is always less than 1 here. And look at this absolute value. If y is less than 1, this is always going to be a positive term, so we don't need those absolute values. So how do we want to solve this? We could swap sides here perhaps. So y is equal to 1 minus e to the negative x. So that looks like the equation of that purple curve on our slope field. All right, and we've got one more thing to explain here. What was the relationship in parts 1 and 2? We had the same constant solution of y equals 1 since dy dx equals 0. All right. 24, I think I chose a problem similar just for some repetition. Notice now that t is our independent variable, so we don't always have dy dx. So y is our dependent variable. So we want to move the y's to the other side and the dt with the t and integrate. And here we don't need that chain rule. The derivative of y is just 1, so no chain rule needed. Here we would do a power rule, add a constant. And then we've got a solution point here of 2, 3. So when we put 2 in for t, we get a y value of 3. So we would have the natural log. Oh, I guess I am going to have a problem here. I should simplify this first and do our exponentiating first. So like I did last time. So here we would have e to the 1/2 t squared multiplied by e to the c1 e to the C1. And that, of course, you can replace with a constant. All right, so we've got absolute value, and this is our constant, times e to the 1/2 t squared. All right, now I'm going to put in our solution point, and we'll have a 3 minus 3 or a 0 there. And we'll put a 2 in here, 1/2 of 4, 1/2 of 2 squared, in other words, but it's going to be equal to 0. So C will be equal to 0. And what happened last time when C was equal to 0? Put it back here. When this is 0, we get a constant solution. So now we simply have absolute value of y minus 3 is equal to 0 times e to the 1/2 t squared. So 0 times anything is just 0. So our constant solution, y is always equal to 3 on our slope field. That's what the solution curve would look like. And our question might have sounded confusing. It says, now find the value of y of 5. Well, we're on a horizontal line, so no matter what the x value is, our y coordinate will be 3. So this is another function where we're looking at the constant solution. And question 25, I wanted to review the vocabulary. The problem, the multiple choice question, might be pretty straightforward, but let's do a good review. So our population grows at a rate proportional to its size. So the rate of growth of the population was our dp dt, change in population with respect to change in time, is proportional to its current population size. So we had our constant of proportionality. And with any luck, you remember when we solved this, that we got a population function that was our basic exponential value. C was the initial population, or P naught, and our K value in both of these is called the relative growth rate. And I hope you will be able to skip right to that solution, but let me remind you. So I'm going to zip through this process of separating the variables to remind you where that came from, and then we integrate both sides, and we have natural log of p is equal to kt plus our constant. And when we exponentiate each side, and you could say, well, if our population is always positive, if there's no negative population, you might not worry about that absolute value. But now when we exponentiate, I guess if I'm showing you, I should show you this step also. E to the kt plus c1 is equal to e to the kt times e to the c1. And then that became our exponential function. And then to find the relative growth rate, so this, if we put in times 0, if you put in times 0, then this becomes 1. So that's why C is our initial population. And we needed a second point to find out what the relative growth rate K is. All right, so now let's go back and look at this specific problem. So the initial population was 400. And we know that after 1 hour, the population was 1,600, so it quadrupled. So we could use this to find our value of K. But we know that the population quadrupled in 60 minutes. So the question says, how many minutes would it take for it to double? So you might already know the answer to this multiple choice question. So you might not have to do all of this work, but I'm going to proceed here. So we know, oh, and I didn't put in my t value here. The t value was that this happened after 1 hour. So if you use hours, this would become t as 1. All right, and then we would say the natural log of both sides. And that would bring our k down in front. So when we take the natural log of both sides, so our relative growth rate is the natural log of 4. So if you were doing the problem with some values that weren't nice multiples, so now that you have this value, I'll put t in front of natural log, you would be able to use that function to predict other values. So if you hadn't noticed the pattern and the question said, when did it double? If you went through this longer process than you needed to, you would be solving this equation. So to get the variable out of the exponent, you would take the natural log of both sides. And the natural log of e, would be a 1. So you wouldn't necessarily write that, but I brought the exponent down in front. So to solve for t, we would have ln of 2 over ln of 4. And not because you can divide those, but because they are powers of each other. So 4 is 2 squared. So only because we could rewrite this denominator as 2 ln of 2. So this is where we would come up with 1/2 hour if we did this the longer method. Okay, but if you had powers, simple powers, you could do that multiple choice question fairly quickly. So I just wanted to use that as a chance to review relative growth rates.